Welcome to the first session today. I'm happy to be the first here. My name is Markus Herdin from the company Rohde & Schwarz, and I'm in an organization called Market Segment Organization, which has an application focus, and my application focus is power electronics. That's the reason why I'm talking about this topic, namely oscilloscopes for power electronics and what they can do. Because I think today they are an kind of almost all-in-one solution for many topics that are important in this application area. If you go through the design flow of power electronics design, one of the first things when you're really designing inverters or converters, so when you care about the switching, when you're not only using modules, is you care about circuit, sub-circuit timing, you care about dead time and so on. And usually you do this in the first step without DC link voltage applied. And then in the next step, if you're sure the timing is correct and you don't have a short circuit or something like that, a shoot through, then you care about FET ratings. What are the voltages that are actually in the designs? What about ringing and those kind of things? Most important topic there is probing, obviously. Yeah. Then, if those things work, often you care about inductors and capacitors. Yeah? So you analyze the behavior of passive components. For example, you want to look like on things, what is actually the inductor current, and is the inductor maybe saturated or not? This is a second step to think about. Then, if the whole system is working, you think about startup variation, startup load variation, efficiency, stability. Usually, the analysis capabilities of the scope are important. And last but not least, you have to check about environmental things. And one of the environmental things is EMI, of course. And then there are only other things like thermal, DC link variations. And a lot of those topics you can cover with with oscilloscopes and corresponding probe solutions. First, I would like to touch the probing topic. One of the interesting things in first hand is floating measurements, because when you have to make measurements on power electronic circuits, they have to be floating usually. First things you can do, but what we cannot recommend, still many people do, is you could float the scope. Yeah? That's a very cheap and easy method of getting a measurement where you can measure anywhere in the circuit. One of the difficulties there is that actually you might get large voltages on the chassis of the instrument, so it can be dangerous. Yeah? And there are some other disadvantages, which I will touch on the next slide. Yeah? So that's the reason why we cannot really recommend for safety reason. There is one exception. Sometimes it makes sense to have a test setup where you have instruments behind the safety screen, and that's of course a situation where you can do that. Yeah? Second method, and this is definitely not recommended because it does not give you good measurement performance, is you could say, okay, let's take channel 1 and 2, and let's just subtract them. Yeah? The problem there is that on the one hand side, probes are not matched, yeah, and they're not matched in frequency response in particular, so results will be very unclear. The second thing is that the resolution of the scope is not sufficient, because each of the signals has to be measured with high resolution, and then you subtract, and the remaining resolution is only very limited. So cannot be recommended because of performance reasons. The usual method to go is use a differential probe, so high voltage differential probe, depending on your design. Big advantages: it's safe, it has good input parameters like low capacity, high common mode rejection ratio. That's the method you use when you use a laboratory scope, a bench scope usually, or you can also work with isolated channel scopes. Yeah? The big advantage of isolated channel scopes is they are much cheaper in a system, yeah, because you don't need differential probes. And using the right connection technique, the actual results can be very good. But if you go up to high switching frequencies, and actually not the switching frequency, but very fast rise times, that's the key point, then there is a point where such a solution is not great anymore. Yeah. Let me touch the isolation transformer topic quickly, the first method that I mentioned. There is one more thing apart from safety, and this is actually to what extent is the measurement really isolated. And when you think about how an isolation transformer looks like, you will find out that there is actually a significant coupling for higher frequencies. Yeah? This means isolation is only there for low frequency. Isolation is very good for 50 hertz or 60 hertz, whatever the distribution, electric distribution network is working at. But if you go to higher frequency, that's not the case. Yeah? And this means now that you have a connection which connects the point here, the measurement point, to ground earth at high frequencies, and can, on the one hand side, lead to wrong measurements. On the other hand side, actually influence your device under test, which again leads to wrong measurements. So that's something to consider, even if you use such a scope in a safe environment behind a safety screen and so on. Yeah? So comparing those methods, quick overview. Number one, so floating the scope is, well, sensitivity is good, accuracy is good, and so on, but common mode rejection ratio is difficult, it's not safe, and you have to consider coupling effects through the isolation transformer. A minus B does not make sense because the quality of the measurement is not good. Yeah? High voltage differential probes is actually a very good method. You can go up to 200 megahertz measurement range. You get a high common mode rejection ratio, and they're safe. Isolated channel scopes are a cost-effective, relatively interesting solution if switching speeds are not so high. Yeah? Bandwidth actually is very high. Sensitivity can be very high, but you have also to consider the connection. Yeah? Okay, what else to look at if you make switching measurement, floating measurements? Well, key consideration, of course, is common mode rejection ratio. And on that slide, there are some thoughts on what is the solution that you need, and what key parameters do you have to consider. Yeah? So the problem, of course, is that, well, one of the most common measurements, you have gate source voltage, measurement of the high side gate, and unfortunately that point here is switching around, sometimes with very high voltage, and you need to suppress this one if you have a differential probe. The first thing you have to think about is what is the rise time of the switch node, and what is the corresponding bandwidth, because this will tell you what common mode rejection ratio, at what frequency you need. Yeah? So let's say you have a slow design, 400 nanoseconds would be a bandwidth of 1 megahertz, 40, 10, 4 nanosecond, very fast design would correspond to a bandwidth of 100 megahertz. Yeah? And I'm using here this kind of estimation, which is fine for this consideration. Yeah? And then you have to think about what common mode rejection ratio do you need. And this depends on the switch node voltage swing. Yeah? And given that you say, okay, 1 volt disturbance on the gate is maybe something that you can tolerate, yeah? Then you would come to common mode rejection ratios of 20, 40, or 60 dBs. Yeah? And those two parameters you can now take and look into the datasheet of the probe and think about, is the probing solution sufficient or right or not? Yeah? Well, and this is what you find in datasheets and also when you do measurements. On the left-hand side, an isolated channel scope. That's the red curve here. And you can see that for low frequencies, so below 1 megahertz, common mode rejection ratio is actually very good. Yeah? And this is true to, well, between 1 to 10 megahertz, it starts to degrade, and then it's not a good solution anymore. Yeah? And coming back to what we had before, this translates to, maybe the point of 10 megahertz corresponding bandwidth is something where you have to think about a different solution. Yeah? I also plotted another curve here, and this is a broadband differential probe. You can see that those probes are usually not designed for such high common mode rejection ratios, But this can be interesting because if the voltage is not so high. Yeah? So the probe that I'm referring to can be used with an additional 10-to-1 attenuator, which gives plus minus 50 volts voltage swing. And with such a configuration, the common mode rejection ratio does not have to be so high, but you can go to very high bandwidths. And you see that 40 dBs are reached at bandwidths of 500 megahertz. So if the voltage swing is not so high, this is an interesting solution. Yeah. When you look at high voltage differential probes, then that's kind of typical common mode rejection ratio versus frequency plots. And you can see that, okay, at 1 megahertz, you have something in the range of 60 dB, and you might remember 60 dB was the first magic frequency that I took. And at 40 dB, you reach speeds up to 200 megahertz, yeah, where the common mode rejection ratio does still make sense, yeah. And this consideration is important for you to understand, okay, does my probing solution fit or not, yeah. Okay, quick comparison. So that was the probe that I talked about as broadband differential probe, and you can see this is this additional 10-to-1 attenuator. And it is an interesting solution if the bandwidth is very high, the voltages are not so high, and you still need high common mode rejection ratio. So maybe that's something that's interesting for gate driver measurements or something like that, but not connected to a high voltage design at the end. This category I introduced here because you actually find different high voltage differential probing solutions in the market. And there's something that I would say is like standard. And when you look at those products, I mean, we also have such products in our portfolio, but they are not really designed for switching analysis. Usually bandwidth is not so high, so it's not the right choice. Yeah? But there's a category which I call like high common mode rejection ratio, high voltage probes, and that is the choice number one if you have a lab scope, a bench scope on your desk. Yeah? Well, then passive probes are here because they are used if you float the scope, or for some, yeah, that's the only reason why it makes sense. Otherwise, you cannot measure with floating. You cannot do floating measurements. The advantage of passive probes in this configuration, of course, is price and bandwidth. That is very attractive in this combination. And an isolated channel probe with, again, passive probes at the end is an attractive choice or trade-off between price and bandwidth if your speed is not so fast. Yeah. Only thing that design is not so fast. Only thing that you have to consider is how to connect them in a good way. Yeah. And that's shown on that slide. That's the other thing that you have to take into account. As usual, you have to make sure that connections are good, so as short as possible. So such a connection is not good because you create a lot of inductance here. At least what you should do is like twist the cables here in order to make sure that the inductance is not so high. And this reductance with the capacitor would create some ringing. That is the way how you should make a connection if you use an isolated channel scope. So like prepare kind of wires on your design so that you can slide in the probe, and that gives high quality connection and good measurement results. Okay, what else to consider? I mentioned MUF functions. MUF functions is something that is sometimes interesting for doing power electronics measurements because they might give you a lot of flexibility or not, depending on the scope you choose. Yeah? An example, measurement that I did here is I wanted to verify currents in parallel MOSFETs. Yeah? And one of the difficulties you sometimes have is how to access the current, how to actually do the current measurements. Standard current clamps are difficult because they are too large. It's difficult to kind of fit them in. So you might use Rogowski probes, yeah, which sometimes fit therein. So there are special Rogowski probes with a very thin wire. Yeah. Well, the other disadvantages or the problem that you have to fight with is Rogowski probes are AC. Yeah. So you have the problem that the signal is floating around. You have to kind of reference it to some point. Yeah? And when you want to look at two independent signals, this becomes even more tricky. Math functions help here, and that's the question of what is the flexibility that you have available. So what I did here is I said, in this double pulse test, I consider the first part here, and I say, I know that the current is here 0 in this particular test here, and I use this fact in order to kind of calibrate my measurement. Yeah? And I'm doing that by measuring the current here and using this measurement in the math function in order to kind of shift the current measurements of the Rogowski probe back to 0 at this first phase. And then the other thing that I did is, because I was able to access one individual current and one sum current, I used the other math function in order to subtract the currents, and that allowed me to get a stable measurements with the two individual currents and to make this verification. Yeah? So main message here is, it is very helpful if you have powerful math functions, because you can do things, you can work around measurement difficulties you have in your design. Yeah? Other things to consider is analysis capabilities, and I have two examples here. One is like PWM or frequency track. So this is sometimes of interest because maybe you want to analyze your control loop and to look at what does the control loop do when something changes. In this example, I was looking at the startup behavior of a resonant converter. So I looked at the half-bridge output, and you can see here a small zoom window which zooms into a very small part of this long capture. So you can see that it's switching here, and in the first phase it actually starts and stops here, so it's not stable yet. And then I looked at the frequency, yeah, because the resonance converter, of course, is frequency modulated, so the frequency determines what amount of energy is transferred. And you can see in the beginning the frequency is not stable. You would find here a frequency maybe in that range sometimes when the switching is working, and then you find this kind of ringing which goes out of the screen because it's a totally different frequency. Yeah? And then at one point in time it stabilizes, and you see the resonance converter, usually it starts at a little bit higher frequency. Yeah? And then it goes down, and then and from here on, maybe you can say it has kind of reached the steady state here, and the remaining variation you see is only the 100 Hertz ripple, which corresponds to the variation in DC link voltage, which translates to a modulation in order to transfer the energy. Yeah? Okay, so that's for that kind of analysis, it's relevant that you have a lot of memory, because usually you want to capture long time periods. In this example, I captured 300 milliseconds, but still you need to look at the details in order to capture the frequency or the pulse width modulation, whatever your design is using. Another thing that is interesting or important is stability of converters. And well, when you look at today's solution of scopes, you find an arbitrary waveform generator, which gives you the ability to integrate such measurements in an oscilloscope as well. Yeah? So we did that, and it's available in several of our instruments, and it basically uses the generator to generate the signal and uses two channels to measure the reaction of the device. Yeah? What you have to do is basically with the generator you're creating a disturbance signal which you feed into the feedback loop, and with the two channels you measure the result. Yeah? And based on that you can make a stability measurement, so a body plot. And that is shown on this example, where I see here the gain curve and the phase curve, and then you can verify, I used here two markers, to verify, okay, what is the phase margin, in this example 36 degree, maybe something where I already feel comfortable, or what is the gain margin, yeah? And that are, I mean, the key considerations here. Big advantages, you don't need a separate solution because you have it integrated in the scope today. Last part is conformance, and one of the important things for conformance, of course, is EMI. It's again the same story. Oscilloscopes today are very sensitive. They only add a little bit of noise floor, and signal processing is fast. So you can perform FFT analysis, and you can also do this in a convenient way. So what is important? The first thing that's important is that you can control it in a sensible way. In the past, you had maybe an FFT button, and then you got a spectrum, and the spectrum depended on what kind of FFT size did you use and what kind of time period did you capture. So it was really difficult to navigate it in a way that you can use it. Today you can do it differently. You can directly enter what is start-stop frequency, what is resolution bandwidth, and you can also use the units that are usually used in EMI compliance measurement, which means that you can do a measurement that is kind of comparable. Yeah? It's not an EMI compliance measurement. That's not possible with an oscilloscope for many reasons, but it gives you an indication where you are, and this is the important thing. Yeah? And the other thing here is, that's of course not possible to show here in the presentation, but you can look at that in our booth. The scope has to be fast enough in order that it makes sense. Yeah? That's in particular true if you do near-field probing, because then you want to have a fast feedback. Yeah? When you move around a near-field probe. It's less important when you look at conducted emissions, because there usually you have kind of a static situation where you look at what are conducted emissions and what is the corresponding spectrum. Yeah? Depending on the scope, there are different capabilities. If you go to like one class higher, you find other things like spectrum masks that you can use to capture things, or you can do more advanced stuff like time-frequency correlation. And I'd like to show you that on that slide. One possibility is to say, okay, your scope adapts record length and everything such that you measure the spectrum and with the resolution bandwidth that you're interested in. But if you have more signal processing power inside the scope, yeah, then you can simply say, okay, let's not only calculate one FFT, but let's increase the record length and let's make frequency selection and record length independent. Yeah? And doing that, you can then say, well, I calculate not only one, but I calculate many spectrums. Yeah? And then you do that, and I plot that into one diagram, and I use color coding in order to display what is the frequency of occurrence of the different spectra. Yeah? And this allows you to see, well, okay, there is something popping up sometimes. Yeah? So you see there is a signal that's sometimes there and sometimes not there. And it looks like something of a clock or data signal in this example. And so that's an additional information that you get. So you see something like the time structure. To some extent, you get more sensitive for short emissions. And you can also do correlated time frequency analysis. And this is shown on the next slide. So given that, you can also say, well, let's restrict the spectrum calculation to a specific time period. Yeah? And let's then move this around. Yeah? And by doing that, you can say, well, maybe I want to understand what is the spectral content that is only in this gate, yeah? Which in this case, I was looking at noise of a DC-DC converter, and no surprise, it looks like noise of a DC-DC converter. Or let's look at the different part of the signal and the spectrum which correspond to this part of the signal, and that's totally different, of course, yeah? And this capability allows you to make something like correlation analysis, understand how does this part of the signal correspond to the spectrum, or vice versa, what part of the signal is creating this disturbance in the frequency domain. Yeah? Okay, that's already kind of last thing that I wanted to show here. Given the scopes that you can choose, I mean, you find different classes of scopes in the market, like for cars. Yeah? There are 2,000 class scopes, there are 3,000 class scope, 4,000, 5,000. And there is this isolated category. When you think about what is the class that I should choose, yeah? 2,000 class is, I think, a very attractive choice if you have no special measurement needs. Sometimes it might be good for production testing, verification. Yeah? You make simple measurements, you find some differential probes for this class of probes. You don't need a lot, and it's available at an attractive price. Still, performance parameters like a deconverter resolution and FFT capabilities are good. Isolated scopes, of course, are kind of a special solution because they have the big advantage of providing differential inputs naturally, and you actually find a lot of performance in those scopes today. Yeah? 3,000, 4,000 class scopes are kind of, from my point of view, the main category that you would use for power electronics design, because you can use all kind of probes. You get all the bandwidth that you need. There are not a lot of people who need more than 1 gigahertz in such instruments for this kind of designs. You get a lot of memory and other capabilities, like these Bode analyzers, for example. And then this 5,000 class, this you would use if you really have a need for very flexible MUF and a lot of other flexibilities, and that makes your life maybe easier. Okay, very last slides. If you're interested in more, because time today was very limited, we have a free seminar tour on oscilloscopes, which is happening in autumn. And it will cover like basics, probing. I just realized it's in German, but anyway, I think most of you are speaking German. It will happen in Germany, and if you're interested, please send an email or get into touch and register. Well, that's all. So there's maybe two minutes. I have maybe time for questions, and otherwise I'm happy to answer questions at the booth. Thank you very much. Okay. Looks like there are no questions, but I'm available, or the other colleagues from our other booth. Thank you very much.